Hey everyone. We're looking at chapter 7 here today. Chapter 7, of course, is going to be our last chapter that we talk about, and this is going to be on conic sections. So basically, when we talk about conic sections, we are talking about what happens when you take a plane and intersect it with a right circular cone, or you can think of it as being a double right circular cone, like you can see in this image over here. So you can basically create a parabola, a circle, an ellipse, and a hyperbola when you are intersecting, like I said, a double right circular cone with the plane. And that's the reason why we call these conic sections, because they're coming from a cone, right? Now, basically, we are saying if the plane passes through the vertex of the cone, then the intersection of your cone and the plane is called a degenerate conic. Okay, so you can see with the different images we have here how each one of these sections are created. So we've got the parabola, we've got our circle, we've got an ellipse, and we've got a hyperbola. So if you actually click on this image, it shows up as a video over here. Oops. Okay, so it will show up as a video, but I already have this set up for us. So if you click on this video, you will actually see a little animation of how these conic sections were created, okay?
Conic sections. In this module, you will learn about conic sections. When a straight line intersects a vertical line at a fixed point and rotates about that fixed point, the surface obtained is called a double right circular cone. A double right circular cone consists of two cones joined at a fixed point called the vertex. The line that rotates about the vertex is called the generator, and the line that remains fixed is called the axis. A right circular cone has a circular base, and its axis is always perpendicular line from the center of the base to the vertex. The perimeter of the base is called the directrix. The lateral surface of a right circular cone is called a nap. A double right circular cone has two naps. The nap above the vertex is called the upper nap, and that below the vertex is called the lower nap. Also, the angle between the generator and the axis is called the vertex angle. Conic sections. If a plane intersects a double right circular cone, we get two-dimensional curves of different types. These curves are called conic sections. Depending on the angle made by the plane with the vertical axis of the cone, the plane can cut the cone in three different ways. Ellipse. When the plane intersects the double right circular cone in such a way that the angle between the plane and the axis is greater than the vertex angle, we get a closed curve called an ellipse. When the plane is perpendicular to the axis, the ellipse becomes a circle. Thus, a circle is a special type of ellipse. Parabola. When the angle made by the plane to the vertical axis is exactly equal to the vertex angle, we get an open curve called a parabola at the intersecting surface of the cone. Hyperbola. The plane intersects only one nap of the double right circular cone as long as the angle between the plane and the vertical axis is greater than or equal to the vertex angle. However, if the plane intersects the vertical axis at an angle smaller than the vertex angle, the plane intersects both the naps of the cone to form an open curve called a hyperbola, which has two disjoint curves. Degenerate conics. If the plane intersects the double right circular cone at its vertex, the ellipse becomes a point, the parabola becomes a line, and the hyperbola becomes two intersecting lines. The figures so obtained are called degenerate conics. In this module you have learned.
Okay, so as you can see, this is a little bit of a longer video, so you can watch it in its entirety if you like, but it has a really good description of how the plane intersects the double right circular conic or cones, and how we come up with our parabola, hyperbola, our ellipse, and our circle, right? The different conic sections. Now, before we continue, I also wanted to show you this little video over here, which talks about how this bobcat makes a perfect parabolic jump. So if you watch the jump that this bobcat is going to make, it's actually going to be in the shape of a parabola. In that same way, if you were to throw a baseball, what kind of an arc that baseball would make is the same thing. It makes that parabolic motion. You have that parabola that is created. So let's go ahead and take a look at this video over here really quickly.
But hunting is hard for a cat that's not used to getting its feet wet.
Okay, so you will see how that cat made that perfect jump over this expanse of water. And I think the cutest thing I have seen is that bobcat, as it shakes its little back feet to get the water off of its hind legs. So I thought that was a cute video, but also it gives you an idea of, we see these shapes occurring in everyday activities in just nature. So, of course, we have had a detailed discussion about parabolas in chapter 2 and 3, but this time we are looking at them more in the geometric sense than in the algebraic sense. So here, when we're discussing conic sections, we're not going to be doing as much of the algebraic calculations, but like I said, doing a little bit more in terms of its geometry. So let's go ahead and take a look at this definition for a parabola here. So of course in section 3.1, we defined our parabola algebraically as the graph of y equals ax squared plus bx plus c, where your a value is not equal to 0, or we also talked about it in the transformation form as y equals a times x minus h squared plus k, right? Now, when we're talking about parabolas in terms of its geometric definition, you are actually not going to have an equation associated with it. So your definition is a parabola is a set of all points in the plane that are equidistant from a fixed line, which will be the directrix, and a fixed point, which is not on the line, that we call as the focus. If you remember in the video that we just looked at for conic sections, they had mentioned the directrix, so you can kind of go back and review that if you like. But basically we are saying that your parabola, and you can see this in the image over here, this parabola, all the points in the parabola are going to be equal distance from this fixed point, which is the focus, and you can see that right over here. And underneath the parabola, we see the straight line, which is our directrix. So basically all the points, if you look at a point over here, its distance to the focus and its distance to the directrix, it's going to be the same distance. If you pick a point somewhere over here, then this distance from the focus and this distance to the directrix is going to be the same distance. So that's kind of how we are defining our parabola in its geometric sense. Okay, so we are saying in terms of the focus and directrix, our axis of symmetry can be described as the line that is perpendicular to the directrix, and it will basically contain the focus or pass through the focus. So as you can see, let me clear out these lines over here. So as you can see, our axis of symmetry is this vertical line that passes through the focus. It passes through the vertex of our parabola, and it's going to be perpendicular to the directrix. So basically that means they will be making a 90-degree angle, right? And of course, we are also saying the vertex is the point on the axis of symmetry that will also be equidistant from the focus and the directrix. So we are saying this distance here between the focus and the vertex, and this distance here between the vertex and the directrix is also going to be the same distance. And this is going to be very crucial when we start looking at examples for these parabolas. Okay, so just some important information that you have in here that you should keep in mind. Okay, so we are going to have our algebraic equations to help us out in solving these. So of course we are given our equation y equals a times x minus h squared plus k. Remember the numbers h and k give us the vertex of the parabola. Okay, now to find the focus, you can actually use the ordered pair h comma k plus p, and the directrix is going to be y equals k minus p. Now remember, focus is a point, so that's why you have an ordered pair. Directrix is a line, that's why we have this equation. And this value p that is basically being added or subtracted from that k term is going to be, if you look at this left hand side image, this p is basically the distance between the vertex and the focus, or the distance between the vertex and the directrix. So that's what this p value is going to be. And then we define p as a equals 1 over 4p, and this a is of course the a value that's coming from our equation for the parabola. Okay, all right, so as you can see in this image over here, if we have a parabola opening up, then your focus is going to be above the directrix. When you have a parabola opening down, which is this image on the right hand side, then the focus is going to be below the directrix. And of course we know when a parabola opens up, we are going to have a positive a value. And since the relationship between a and p is a equals 1 divided by 4p, that also means that our p value has to be positive. If a parabola is opening down, that means our a value is negative, which will also mean that our p value is going to be negative. So you can kind of see this image, and you can see how these calculations work out to be. So since your vertex is at hk, to find the focus, we keep the same x value so that h variable stays the same. But since the focus is going to be above the vertex, we add k plus p to get the y coordinate for our focus. To get the directrix, because the directrix is going to be below the vertex, we do k minus p, and then remember in this case p is a positive value. When the parabola is opening upside down, again our vertex is at hk, but now that the focus is going to be underneath the vertex, we are still using the same form, h comma k plus p, but remember here p is going to be a negative value. And then for the directrix, with the directrix being above the vertex, same formula, y equals k minus p, but since p is going to be a negative value, you essentially end up adding p over here, and you end up subtracting p in your focus. But of course, when we do the examples, you'll get an idea of that. Okay, All right, so they're saying for any particular parabola, A and P have the same sign. So like I showed you here, if it opens one up, A and P will both be positive. If it opens down, A and P will both be negative. So they will always have the same sign. If both values are positive, parabola opens upward. If both values are negative, your parabola opens downward. And if the parabola opens 1, then the focus is going to be above the directrix. If the parabola opens down, then the focus is going to be below the directrix. And again, you can kind of look at the two graphs over here and verify that. So for our first problem, they are asking us to find the equation when they are giving us the focus and the directrix. So we are given the focus and the directrix, and based on that, we need to come up with the equation for our parabola. So let's see how we can use this information to help us out. Okay, so remember, your focus gives you the h coordinate, which is of course our number 3, and the 5 is going to be our k plus p value. Directrix, remember our equation is k minus p, which gives you the directrix. Okay, so at this point, we have no idea if our parabola is opening up or down. We don't know if our p value is going to be positive or negative. But you know what you can do is do just a very rough sketch over here. Okay, so let's see. Our focus is at 3, 5. So that's 1, 2, 3, 2, 3, 4, 5. So 3, 5, this is where our focus is going to be. And the directrix is the horizontal line which is passing through y equals 2. So y equals 2, of course, is going to be this one right here. So as you can see, my focus is above the directrix. This actually tells me that our parabola basically opens up. Oops. Okay, so parabola opens up, which tells us our A value has to be positive, which means the P value also has to be positive. Okay, now remember the coordinates for the vertex of our parabola are at HK. So of course we have the H value right here from the focus, so that is going to be our H value is going to be 3, which means we just need to find our K value, and you are essentially going to try and find all of these values in our transformation form. So we already know H, we need to find the K value, and we need to find the A value if we are going to come up with the equation of our parabola over here. So like I said, we already know H is 3 because we are getting that from our focus, but we need to figure out what the other two values are going to be. So this is where we are actually going to use this idea where K plus P equals 5 and K minus P equals 2. So we are actually going to be solving this like a system of equations. So K plus P equals 5, K minus P equals 2. So if we just go ahead and add these two equations, that positive P and negative P will cancel out, right? Just like we saw in our chapter 5. And then we can go ahead and add K plus K, which will be 2K. 5 plus 2 will of course add up to 7. Divide both sides by 2 to get our K by itself. And of course that will end up giving us 7 over 2. And of course these guys cancel out over here. Okay. So we have our K value. So K is going to be 7/2. Now that you have found the K value, we can go back to any one of these equations and find what our P value is. And we need the P value because we will use this relationship. Oops. Okay, so we're going to use this relationship of A equals 1 divided by 4P to help us come up with the value of A. So that's why we need to find P over here. So I guess I can use k plus p equals 5 to find our p-value. So k is 7 halves. So subtract 7 halves from both sides. And we end up getting p equals 5 minus 7 halves. When you find your common denominator, 5, of course, here we would multiply by 2. So you would end up getting 10 over 2 minus 7 over 2. And that, of course, comes out to be 3 over 2. So that's going to be our p-value. So we have k, we have p, and now we can find the a value, which is a equals 1 divided by 4p. So 1 divided by 4, and for p we have 3 halves. Now again, guys, you can see that we have 4 times 3 halves, so 2 can go to itself once. 2 goes into 4 2 times. So that will actually end up giving us 1 over 2 times 3 will become 6. So you get a equals 1/6. And you can always plug this into your calculators, but just make sure you don't leave them as decimal answers. We do not want decimal answers. We want fractions, reduced fractions in our equation over here. Okay, so now we also have our a value, which is 1/6. So once you have all your a, h, and k, you are ready to find what your equation is going to be. And since we already know our k value is 7 halves, that means we also know where our vertex is going to be. And your vertex is going to be at positive 3. And 7 halves is, of course, 3.5. So right here, halfway between the directrix and the focus is going to be your vertex. So this is kind of where that parabola would be at. Now, of course, we don't know the graph of it, so I'm not going to graph the entire thing, but this at least gives you an idea of at least what the graph would end up looking like. All right, so let's put our equation together. So we've got a as 1/6. We've got h as 3. And we've got k as 7 halves. Okay? Now, if your instructions say to leave it in this form, you can, but if they ask you for the standard form, and the standard form, remember, is y equals ax squared plus bx plus c, then we will need to simplify this further. So of course, the first place we would need to start is right here. We would need to FOIL this. So when you FOIL this, you should end up getting x squared minus 6x plus 9. So that's going to be 1/6 x squared minus 6x plus 9 plus the 7 halves on the outside. And then we would need to go ahead and distribute this inside the parentheses, which would end up giving us 1/6 x squared minus 1/6 times 6x plus 1/6 times 9 plus the 7 halves. So the 6 in the denominator and the 6 from the 6x will cancel out. 6 and 9 will have 3 in common. So 3 goes into 6 twice. 3 goes into 9 3 times. So you would need to simplify each of these terms. We would have 1/6 x squared from the first term, minus x from the second term, plus, let's see, these guys, and you can write this as 3 over 1 if it helps. These guys will end up becoming 3 over 2 plus 7 over 2. And then again, we need to combine like terms. So it looks like we will end up getting 1/6 x squared minus x plus, when you add 3 halves with 7 halves, since they already have the same denominator, you just end up adding 7 plus 3, which gives you 10. 10 divided by 2 will of course give you 5. So in standard form, our equation will look like 1/6 x squared minus x plus 5. Okay, so just depending on if they want us to leave the answer in the transformation form, which is this guy here, or if they say to put it in standard form, then you would need to simplify your answer. But that's basically how you find the equation of your parabola when you are given the focus and the directrix. Okay? Alrighty. Now, the other thing I wanted to mention before we move on from here is basically remember between the y value from our focus and the value of your directrix, your k value or the vertex is always going to be halfway between that. So you could have basically just added 5 plus 2, 7 and divided by 2, which would have also given you this k value of 7/2. So as long as you remember that halfway between this distance, which is from the focus to our directrix, halfway between that is where your vertex is going to fall, so you can get your k value that way also. And if not, then you need to go about doing it like the way I showed you here. Alrighty, so that was our example 1. Okay, so again, remember the standard form for the equation of our parabola is going to be y equals ax squared plus bx plus c. They are saying that you can basically identify where the focus, vertex, focus, and directrix is going to be if you rewrite it into the transformation form. So you can take your standard form and rewrite it into the transformation form to find out what the vertex, focus, and directrix of the parabola is going to be. So here, in example 2, same thing. They're asking us to find the vertex, focus, and directrix if we are given the equation of our parabola in the standard form, y equals 2x squared plus 4x minus 1, and they're asking us to do this in 2 different ways. So the first method, they're asking us to do this by completing the square, and for the second one, they are saying do this without completing the square. So how can you find the vertex, focus, and directrix in these 2 different methods? And then at the end, they also want us to determine if the parabola opens up or down. Okay? Alrighty. So let's go ahead and take a look at this example over here. So y equals 2x squared plus 4x minus 1. So of course you can see our a value here is a positive number. So since a is a positive number, because of course a equals positive 2, then that means our parabola opens upward. And if the parabola opens upward, that means the focus is going to be above the directrix. Okay. Alright, so first method we are going to look at is by completing the square. And you had actually seen this method in section 3.1. Okay, so our equation is y equals 2x squared plus 4x minus 1. So this is where, remember, we take the first 2 terms. Since my leading term x squared has a 2 in front of it, I'm going to take the 2 outside as my greatest common factor. So that will leave me with x squared plus 4 divided by 2 leaves us behind with 2x minus 1. You'll see I didn't take my x outside, right? Just the number 2. And then this parentheses part is where we are trying to complete the square. So this is where we take our b divided by 2 and then square the entire thing, right? So inside the parentheses, my b term is 2. So 2 divided by 2 is going to be 1. And then 1 squared, of course, is going to be 1. So inside the parentheses, To complete the square, we add the 1. But to maintain the balance of our equation, we subtract the 1 also at the same time, and then don't forget that minus 1 at the end. Now we only need to keep the first 3 terms, which means I don't need this negative 1 which is inside my parentheses. So I need to bring this negative 1 outside. So what we do is we multiply this negative 1 with this 2 in the front. So you multiply these two numbers, and that's how we bring it outside. So I'll keep my first terms the same. So 2x squared plus 2x plus 1 will stay as it is. And now that I'm bringing this negative 1 outside, that's going to be 2 times negative 1, which is negative 2, and then don't forget this negative 1 at the end. Okay, so now you can go ahead and factor this, and this will factor into x plus 1 squared, and then negative 2 minus 1 at the end will end up becoming negative 3. So again, remember, with this parentheses part here, x squared plus 2x plus 1, it basically factors out into the same expression, because remember, we made this into a perfect square trinomial. And to help you out, you can always think of this number 1 over here. So right before, when we squared it, whatever is inside the parentheses, that's what your number is going to be right here when you factor it. And of course, it comes out to be the same factor. And so that's where you get x plus 1 squared from. So now that we have rewritten our equation from the standard form to the transformation form, we can now go ahead and identify our vertex. So remember, our vertex is going to have the coordinates hk, which in this case our h is here and our k is here, so that will come out to be negative 1 for h, negative 3 for k. Now remember guys, when your equation is in the general form for the transformation, you always have x minus h. So that means if h itself in this case is going to be positive, but if h is negative, then your equation basically becomes a x plus h squared plus k. So if you have a plus sign here, that means the h itself is negative. If you have a minus sign in your parentheses, that means your h is positive. So you always have to go with the opposite sign. So since this was positive 1, that tells us our h value is negative 1. For the k, you always keep the same sign, negative 3, so it will stay as negative 3. Alright, so once you have found your vertex, then we can go ahead and find our focus and the directrix. Now remember, the focus has the ordered pairs h and k plus p. The directrix has the equation y equals k minus p. So we know the focus also has h as its x coordinate, which means we will still have negative 1 over here, but now we need to find what k plus p and k minus p is going to be. So for that, we of course need to figure out what our p variable is going to be. So this is where again we go back to that relationship between a and p, which is a equals 1 divided by 4p. Now of course we know our a value is going to be right here from the leading number in our transformation form, which is positive 2. So if a is 2, you can work backwards to find p. So I'll go ahead and multiply both sides by 4p. These guys cancel out here. We are left with 4 times 2 is 8p equals 1. To get p by itself, go ahead and divide both sides by 8. And you get p equals 1/8. Okay, so now that we know what the p value is, we can go ahead and calculate k plus p and k minus p for the focus and the directrix respectively. So our k value is negative 3. P is 1/8, and then of course we'll simplify that. For the directrix, you will do k minus p, so that's negative 3 minus 1/8, and this will come out to be -1 comma, let's see, -3 plus 1/8. So put this on a denominator. We need to find our common denominator. So that's going to be -24 plus 1/8, which comes out to be -23/8. So that's going to be -23/8 for our focus. Now let's see, for our directrix, we will do -3 minus 1/8, which will of course be the same thing. Find your common denominator. This will end up giving us -24 minus 1/8, which of course comes out to be -25/8. So -25/8. Okay. And you know, if it helps to write this as an equation, that should be y equals -25/8. So we've got our vertex, we've got our focus, and we've got our directrix. This is what they were asking us to find in this equation. Now they were of course asking us to do this in two different ways, by completing the square and without completing the square. So we've done the completing the square part of it. Now of course we need to do how you would do this without completing the square. So that's our second method. And you know, without completing the square, again, this is the exact same thing you saw in chapter 3. We will calculate our vertex by using the equations -b/2a, and then you put this back into your function to find the y value. So since we are given y equals 2x squared plus 4x minus 1, right? So to find our x coordinate for the vertex, it's -b/2a. So that's going to be negative. Of course, our b term is +4. A term is 2. So that would be -4 over 2 times 2, which is -4 over 4, which of course comes out to be -1. So you are getting your vertex as -1, and now to find the y value, we put this back into our equation. So that's 2 times -1 squared plus 4 times -1 minus 1. And let's see, that will come out to be 2 times, because -2 times -1 times -1 will become +1. So that's 2 times 1, so that'll be a 2. 4 times -1 will become -4, and then minus 1 at the end. So let's see, that's going to be -2 minus 1, which will be -3. So our y value is coming out to be -3. So we've got our x for our vertex, and we've got y for our vertex. So once you find the vertex of -1, -3, then you are basically going to repeat the same process that you did over here to find the focus and the directrix. Of course, we would start by finding our p-value first, and then once you found the p-value, you would take k plus p and k minus p to find the coordinates for your focus, and then the equation of your directrix. So of course it will lead you to the same process here. So then find the focus and the directrix like we did above. So that process will stay the same. So it's just a matter of how do you find your vertex. So either use the standard form of your equation and go by using this formula, x equals -b/2a, find your x coordinate, then come back and find the y, or you can do completing the square, which is what we did here, and then of course using the h and k values from here, we came up with our vertex. So that's the two different ways you can go about solving this example number 2. Okay. Alrighty, now let's talk about how can we graph these parabolas based on their geometric definition. So again, remember we are saying by the geometric definition that every point on the parabola is equidistant from its focus and directrix. So they're asking us here to find the vertex, axis of symmetry, the x and the y intercepts based on the focus and the directrix that is given to us, and they're asking us to sketch the graph, and they also want us to show the focus and the directrix on the graph itself. So let's go ahead and take a look at this example over here. So we are given the focus as -1, comma 35/4, and we are given the directrix as y equals 37/4. Okay. So the first thing we need to do is figure out where the vertex of our parabola is going to be. So remember, this is again the h and the k plus p coordinates here, and this of course gives you the k minus p value from here. So if you look at decimal approximations for 35/4, it's actually as a decimal, this number is 8.75, and 37/4 is going to be 9.25. Okay, so if you think about this, halfway between 8.75 and 9.25, we should have our y coordinate for the vertex. Because remember, the vertex is at hk. Your h value, of course, is -1. So this is going to be -1, and we just have to figure out where k is. So if you take your 8.75, add it with 9.25, and then divide by 2, that will give us 18 divided by 2, which gives you 9, and that's going to be our k value. Okay, so this is kind of what I was talking about in example 1. So that means my k value is 9. This is where my vertex is going to be. So at -1, 9 is our vertex. Now this is going to be the hard part, because at 8.75 is our focus, which is going to be right over here, and then at 9.25 is our directrix, which is of course going to be this horizontal line. So this is y equals 37/4, and then this point over here is our focus, which is, let's call it point F. So our focus is going to be at -1 and 35/4. Okay, and this one of course is our directrix. But now that we have our vertex, they were also asking us to find the axis of symmetry and the x and y intercepts also. Now remember, axis of symmetry always passes through the vertex and the focus. It's going to pass through the x coordinate of our vertex and our focus. So that tells us the axis of symmetry is going to be the line x equals -1. So that's actually going to be, and I guess I'm going to use green for our axis of symmetry, and it's going to be this vertical line that will pass through the focus and the vertex, and of course it's going to be perpendicular to our directrix. So this here is our, oh, I guess I don't really need that. This one here is our axis of symmetry, which is going to be at x equals -1. Alrighty, now let's see how we can go about finding our x and y intercepts. Now for the x and y intercepts, we are of course going to need our equation to be able to come with that. So we already have our h and k values because we can of course get that from the vertex of our parabola here, and we already calculated that. So what we need is the a value, right, to come up with our equation. So what you need to see here is what is going to be this p-value, because we didn't officially calculate p. But remember, p-value is the distance between the focus and the vertex, or the distance between the vertex and the directrix. So think about this. If the y-coordinate of my vertex is at number 9 and my focus is at 8.75, so the distance between 8.75 and 9 is going to be 0.15, right? So you can think of this as 0.15, or basically as a fraction, as 1/4. If you again look at the distance between 9, which is my k value, and the directrix, which was at 9.25, again the difference between 9 and 9.25 is of 0.25, which again is going to be 1/4 as a fraction. So you actually just can calculate the value of p just by looking at the distance between the focus and the vertex, or the directrix and the vertex. Alright, so now let's go ahead and find our a value, which will be 1 divided by 4, and then for p we have 1/4. So again, you can think of these 4 and 4 canceling each other out, basically giving us 1/1, or the value of 1. So a comes out to be 1, and now we can put this in our equation. So let's see, the equation will come out to be y equals, a is 1, so you can just leave that as it is, x, h is -1, which means this will be +1 squared, and then k is +9, so this will be +9. So this is going to be the equation of our parabola. And once you have the equation, you can go ahead and find your x and y intercept. So let's start with the x-intercept, and that means we need to make the y value 0. So that will be 0 equals, oh, hold on a second, I did something wrong. Oh, yeah, so you can see my focus is actually below my directrix. Okay, so since our focus is below the directrix, this tells us our parabola opens downward. So since it opens down, that means our a value is going to be negative and our p value is going to be negative. So this should actually be negative. Let's rewrite this. This should be negative 0.25, or -1/4. So that means our a value will actually also end up becoming -1. So this should be -1. Sorry about that, I was not paying attention. So that means this will be negative here. Okay. Alright, so negative over there, so we should have negative x plus 1 squared plus 9. Alright, so coming back to our x-intercept, so we are trying to find the value of x. So let's try and get x by itself. We'll start by subtracting 9 on both sides. We get -9 equals negative x plus 1 quantity squared. So now we can go ahead and divide both sides by -1 to get rid of this negative sign. And we will end up getting 9 equals x plus 1 squared. To get x by itself, we'll go ahead and take a square root on both sides, which gives us a positive and a negative root. So that's positive or -3 equals x plus 1. Subtract the 1, and we should come up with two different answers for our x. So that will be +3 minus 1 and -3 minus 1. And what will that give us? So let's see, we should end up getting 3 minus 1 should be 2. -3 minus 1 should be -4. So you are looking at 2, 0 and -4, 0 as the x-intercepts. Okay, so 2, 0, -4, 0. So that's going to be right here. 2, 0 and -4, 0, where we have our x-intercepts. Okay. Alrighty, and then let's see, our vertex is at -1, 9. Alright, the next thing we want to do is find our y-intercepts, or intercept, which means we make our x value 0. So y is going to be negative x plus 1 squared plus 9, but this is where we make our x value a 0. So that would be -1 squared plus 9, which is of course -1 squared would just be 1 plus 9. So -1 plus 9 comes out to be 8. So y-intercept is actually going to be at 0, 8. So let's see, 0, 8. Will be right over here. And if you use the idea of symmetry, then you should have -3, 8 also as a point on the line. Sorry, -2, 8, not -3, 8. -2, 8, there we go. And then this here was our focus. Okay, so if we use those points to give us a shape of the graph, something like this will be the graph of our parabola, and this is the equation y equals negative x plus 1 squared plus 9. Okay, so I hope you can kind of see what this equation comes out to be, how we calculated our x and y intercepts after you found the equation. Now, the one thing I do want to reiterate, since I forgot doing that also, is once we graph our directrix and our focus, we should have actually noticed it right away and I didn't even pay attention, but since the focus was below the directrix, that told us that our parabola was opening downwards. So that means our A and P, both of those values were going to be negative. Okay, so again, look through this example. Alright, now I did want to talk about, what happens when our parabola is opening to the left or right, because in that case, your x and y values will switch places. So, of course, when your parabola is opening up, we have y equals 2x squared. But like I said, if you switch your x and y values, then you actually end up getting x equals 2y squared, which will also be a parabola, but in this case, it will actually be opening to the right. Okay? So they're saying just interchanging the variables simply changes the roles of the x and y axis. 2y squared, 2y squared. Y equals 2x squared would open up, but x equals 2y squared would open to the right. So if your parabola is opening to the left or the right, that means our directrix will now become a vertical line. And that actually tells us then your axis of symmetry will become a horizontal line. They're saying if the focus is to the right of the directrix, then the parabola opens right. If the focus is to the left of the directrix, your parabola opens left. So your equations for parabolas opening right or left will be x equals a times y minus k squared plus h. So you will notice our h and k have also switched places. And in the standard form, it would be x equals ay squared plus by plus c. Okay? If this a value was going to be positive, then the parabola would open to the right. If the a value was negative, parabola opens to the left. Okay, now since your x and y also interchange, that means negative b over 2a will now be the y coordinate for the vertex. And like I said, your line of symmetry or axis of symmetry will become a horizontal line, which would be at that same value of y equals negative b over 2a. And so you can kind of see what these graphs would end up looking like. Focus is to the right of the directrix, so parabola is opening right. Focus is to the left of the directrix, so parabola opens left. Our vertex is still at hk. Directrix is now going to be x equals h minus p. Focus is going to be h plus p comma k. And then of course this is the equation of our parabola opening to the right when a is positive. Same thing here, focus is going to be h plus p comma k. Directrix is x equals h minus p. Vertex is hk. And the equation of our parabola when a is negative. So they're asking us to find again the focus, axis of symmetry, x-intercept, y-intercept, the focus and the directrix also when they give us the equation of the parabola as x equals y squared plus y minus 6, and then they're of course asking us to sketch with the focus and the directrix also. So let's go ahead and see all the information that we have and what we need to find. So x equals y squared plus y minus 6. So as you can see here, our a value is going to be 1 because that's the coefficient on your y squared, which is 1. So since this is a positive number, that means our parabola opens to the right, which also means the focus is going to be to the right of the directrix. Okay, so that kind of at least gives us an idea of how this will end up looking like. Now let's go ahead and find the vertex of our parabola over here. So remember, since this is going to be a parabola opening to the right, your vertex is going to be y equals negative b over 2a. So of course you can see our a value is 1. Our b value will also be positive 1. So this will be negative 1 over 2 times 1, which basically gives us negative 1/2. Once you find the y coordinate, we can go back and find the x coordinate by plugging this into our equation. So x equals y squared plus y minus 6. So this will end up becoming negative times negative becomes positive. 1/4. This will become negative 1/2 and negative 6. So we need to find a common denominator for all of them. The 6 over 1, multiply that by 4. The negative 1/2, multiply that by 2. And we will end up getting 1/4 minus 2 over 4 minus 24 over 4. So now that you have a common denominator, you can add all the numerators. So 1 minus 2 is negative 1. Negative 1 minus 24 will end up giving us negative 25. And this is going to be, for our x value. Okay. Alrighty, so this is going to be, and you still have to write your ordered pairs as x, y. So the vertex is still going to be hk, which is going to be negative 25 over 4 and negative 1/2. Okay, so let's see, so we can graph these, what the decimal approximations for this guys will be. So negative 25 over 4 is actually going to be negative 6.25, and negative 1/2 of course is going to be negative 0.5. So this will help us in the graphing. So negative 6.25 and negative half. Okay, so that's 1, 2, 3, 4, 5, 6, so quarter and a negative half. Somewhere over there is where the vertex of our parabola is going to be. So this here, the vertex is at negative 25 over 4 and negative 1/2. Okay, now of course our axis of symmetry is going to be passing through the y-coordinate of our vertex, because again this is a parabola opening to the right, so your axis of symmetry is going to be at y equals negative 1/2. So on the graph, that's going to be a horizontal line now. So this is the axis of symmetry at y equals negative 1/2. Okay, now that we have the equation of our parabola given to us, we can find the x and the y-intercept. So that's x equals y squared plus y minus 6. Let's find our x-intercept. This is where we would make the y value 0. So that would be x equals 0 squared plus 0 minus 6. So we end up getting x equals minus 6. And that will be minus 6, 0 as the ordered pair. So minus 6, 0 will be right over here. So minus 6, 0 as our x-intercept, and there will only be one. Now let's find our y-intercepts. This is where we would make our x value 0. So 0 equals y squared plus y minus 6. We should be able to factor this. So two numbers that multiply to give us negative 6 but add up to give us positive 1. So that would be 3 and 2, and we can make 2 a negative number. So 3 times negative 2 is negative 6. 3 plus negative 2, of course, is positive 1. So we would end up getting y plus 3 and y minus 2 as our two factors. Okay, and then you take each factor, set it equal to 0, and we will get y equals negative 3 from here, and y equals positive 2 from the second one. So that should be 0, negative 3, and 0, positive 2 as our two y-intercepts. So at negative 3 and positive 2. So negative 3 and positive 2 are the two y-intercepts. Okay, so again, if I have negative 6, 0 here, then at 1, at negative 6, 1, I should have my symmetric point for the same point. So add negative 6 and negative 1. So our graph would now be passing through. No, I think I did that wrong. because this is going to be my vertex. And let me see, that is, no, that one was correct. Okay, so this will be going like this, and this would be going like this. There we go. Yeah, so -6, -1 would be the symmetric point for that. And this is our x equals y squared plus y minus 6 graph. Now we still have to do, we did the vertex, axis of symmetry, x and y intercepts, but we haven't figured out our focus and directrix yet. Alright, so let's go ahead and do that next. Okay, so we already have our a value. Our a value equals 1. So based on that, we can calculate what p will be. So let's say a equals 1 divided by 4p. If a is 1, multiply both sides by 4p. So these guys cancel out. We are left with 4p equals 1. Divide by 4 to get p by itself. And we get p equals 1/4. Now once we have the p value, then we can find our coordinates for the focus and the directrix. So let's start with the focus first. Now remember, the focus, when your parabola is opening to the right, is h plus p comma k. So remember, our h and k values we can get from the vertex. So our h is -25/4, k is -1/2. So that's h plus p, which is the 1/4, and then the k is -1/2. So of course you can see we have the common denominator 4. So -25 plus 1 will be -24. Oops, sorry. And -1/2, and then of course you can reduce. -24 goes into 4 6 times, so that'll be -6 and -1/2 for our focus. And then for the directrix, again remember, directrix is going to be x equals h minus p. So x equals h minus p will be -25/4 minus 1/4. So that will be -26/4. You can reduce that down, which comes out to be -13/2. Okay, but again, we'll do a decimal approximation for that. So -13/2 is same as -6.5. So let's see, at -6 and -1/2, we have our focus. So -6, -1/2 is going to be right over here. So this is our focus. Okay, so the focus is going to be at -6, and then your directrix was at -13/2, or basically at -6.5. So that's going to be, oh, I'm probably not going to be able to do it because these numbers are so close to each other, but this is going to be a vertical line. Okay, so this is going to be our directrix, and the directrix is at x equals -13/2. Okay, so there you go. So we have our vertex. There we go. This is our vertex right over here. We have our axis of symmetry. We have our x-intercepts. We have our y-intercepts. And Now we have our focus and our directrix. And we were able to graph our function and show those, even though you can't really see them too well, we were still able to at least put them on our graph. So that's kind of how your parabolas opening to the left or right would work out to be. Okay? Alright guys, so the last thing I wanted to talk about here was just an application with this idea of parabolas. So here we're saying in section 3.1, we saw an important application of a parabola, and that was basically how to maximize or minimize data based on our needs. Now in this section, since we are of course talking in terms of the geometric definition of a parabola, we are going to look at a different property here. So in this section, we're actually interested in how does reflection work with light or sound waves on a parabolic surface. So they are saying when a ray of light traveling parallel to the axis of symmetry. So just here you can see in green we have our axis of symmetry. So what happens if you have rays of light traveling parallel to the axis of symmetry? So of course your axis of symmetry would be this line over here. So if you have ray of light traveling parallel to the axis of symmetry and it hits this parabolic reflector, what's going to happen is you will notice that these ray of lights are coming down this direction. They're hitting our parabolic surface and you will see they get reflected towards the focus. Look at any of these lines. They're coming down, they're hitting that parabolic reflector, and they're getting reflected towards the focus. And this is actually going to be an important feature when we talk about telescopes. So we use this property in telescopes to magnify the light coming from distant stars. You can also think about this in spotlights. What happens is your light source is actually at the focus. So that means, let me get rid of these lines over here. So what that means is that basically when the light is at the focus, that means your light is starting right over here. So these arrows are basically going to reverse. So if this is my spotlight, then my light will come and hit this reflective mirror, and then it will basically get bounced out. So these lights will come, hit our reflective surface, and they will get bounced out, and that's why we see the brightness that comes from the spotlight. So this is the reflective property working in reverse when you have spotlights. They are saying light originating at the focus is reflected off the parabolic reflector and projected outward in a narrow beam. Okay, this reflective property is also used in telephoto camera lenses, radio antennas, satellite dishes, eavesdropping devices, and flashlights. So think about satellite dishes. In a satellite dish, you will see how you have that little receiver. So that receiver is actually placed at the focus for that parabolic surface. So the idea is when you receive, your signal from the satellite, the idea is the signal is going to bounce off that reflective surface of your parabola, which is the satellite dish, and it's going to be reflected towards that sensor so that you can read your signal. So that's kind of how radio antennas, satellite dishes, all of them work in that same way, and even the eavesdropping devices. Okay, so they're saying the Hubble Space Telescope uses a glass mirror with a parabolic cross section, and it has a diameter of 2.4 meters. The focus of the parabola is 57.6 meters from the vertex. So that's basically when you're talking about the focus being 57.6 meters from the vertex, this is actually that distance P we have been talking about. Okay, and there's actually a really neat story about the Hubble Space Telescope. I don't know if you guys have heard that or not, but when they were manufacturing the mirror for the Hubble Space Telescope, they had to be so accurate in micro measurements that even if as they were shaping that glass, if even a slightest anomaly happened where they made a mistake, then the Hubble wouldn't work. And that's actually what happened. So they, designed this whole telescope, they launched it into space, and when they first started getting images from the Hubble Space Telescope, they were all blurry. And you couldn't see anything, you couldn't make out anything. And obviously, NASA and all the scientists were really wondering what happened. And that's when they realized that when they were shaping that mirror, they got that reflective curve just a little mismatched to their calculations, that they were not able to focus those images, and obviously the mirror was not working. So they actually had to design a second mirror, and they use, and you will actually see this when we get to section 7.3, where we talk about combining a hyperbola with a parabola, and to see how we can use those reflective surfaces. But basically they had to place a second mirror to shorten that distance between the parabolic glass surface and its focus, where the focus would be, to adjust that image. And of course now, as they say, the rest is history, because we have seen so many beautiful images coming from the Hubble Space Telescope, and we have explored so much of the universe that we wouldn't have been able to. Now, of course, the Hubble Space Telescope is going to be retired here in the next couple years, because they are going to be launching the Webb Space Telescope, and of course that one will replace the Hubble. So this is kind of a neat story of how just a little miscalculation can basically be such a disastrous result, because you spent millions of dollars on this project, and then of course it didn't come out to be the way you wanted it to be. So this little graph over here is just kind of showing you that if you think of this here being at the origin 0, 0, then they're telling us the diameter of the glass mirror is 2.4 meters. So that's basically 1.2 meters to the right and 1.2 meters to the left. And then from the vertex, we are talking about this distance being 57.6 meters. So they're just kind of showing you what the cross section of this parabolic mirror would end up looking like. Now we actually have an example that we want to work through, and this one is talking about the focus of the Hale telescope, and you can see that in the figure over here. On Palomar Mountain in California is 55 feet. So they're saying from the vertex to the focus, that is a distance of 55 feet. So remember, this is going to be our p-value. And they're telling us 55 feet above the mirror. Okay, so we know that. And then they're saying the Pyrex glass mirror is 200 inches in diameter. So they're talking about this glass mirror over here, which is 200 inches in diameter, and they're telling us the glass itself is 23 inches thick. So that's the thickness of the glass, which is 23 inches thick. And they're basically saying find the equation of the parabola that was used to shape the glass, and how thick is the glass on the outside edge. Okay, so the outside edge that they are talking about, this thickness here is actually the center thickness of your glass, which is 23 inches. But if you look carefully, and let me see if I can make this bigger, there we go. If you think about this thickness here, okay, so we have this thickness in the middle, which is 23 inches. But if you look at the outside edges, that glass mirror is going from here to here. So this thickness is going to be bigger than 23 inches. It's going to be thicker on the outside edges than 23 inches. So that's the thickness they're asking us to find. So they're asking us to find the equation of the parabola and what the outside edge thickness of the glass is going to be. Alrighty, so one thing you should notice here is for the Pyrex glass mirror, we are given inches as our measurements, but the distance from the vertex to the focus, we are given as 55 feet. Okay, so that's one thing we're going to need to fix over here. So let's start with, and we're going to assume here that our parabola opens up because that's how we have our graph over here. So we are going to say the parabola opens up, which means our A value is going to be positive and our P value is going to be positive. Now we know the P value is 55 feet, and that's coming from here, but we need to convert this into inches. So basically 1 foot has 12 inches, so that's the calculation we're going to use. So basically this will help us convert it into from feet to inches, and 55 times 12 will end up giving us 660 inches. So rewriting this in inches is going to be 660 inches for our 55 feet. Okay? Alrighty, the other thing we are going to assume is that our vertex is going to be at the point 0, 0. So that's going to be our H and K value, because this is a mirror inside a telescope, so you don't have to be at a certain point. You can assume that if this was on our X and Y coordinate scale, we can place our vertex at the origin, right, at 0, 0, which would make our calculations a lot easier. So remember, they're asking us to come up with the equation of our parabola. So of course, for the equation of our parabola, we need the y equals a x minus h squared plus k. So if we can have our h and k values coming from the vertex at 0, 0, since that's where we're placing our vertex at, then that means we just need to find where a is. And since we know the p value, we can use 1 divided by 4p to come up with the a value. So that would be 1 divided by 4 times, and of course we'll keep everything in inches. So that's 660, and you will end up getting 4 times 660 as 2,640. Okay? So if this is our a value, then let's see what the equation of our parabola will come out to be. Now if you think about this, guys, this is 1 over 2640. Our h value is 0. Our k value is 0. So that will basically come out to be x minus 0 would be x, and that would be squared, and then plus 0 of course would disappear. And so you're really only going to get the equation in the form of y equals a x squared in this case. Okay? Alrighty, so we have the equation of our parabola. So this is the equation that they used when they were designing that parabolic mirror, or I guess it was a Pyrex glass mirror. Yeah, the Pyrex glass mirror for the telescope. Okay, so we have our equation. Now let's look at what that thickness is going to be. Okay, so that's the thickness at the outside edge of our mirror. Okay, so let me go back to, let's actually go back to this guy over here. Okay, and I'm going to go ahead and clear out all of these lines that I drew. Okay, so if you think about this thickness here, just this thickness, is going to be 23 inches, right? Okay, so this thickness is 23 inches. We already know that. What we really need to find is what this little bit of thickness here is going to be. So this is where actually the equation of our parabola is going to come into play, because if we can find out what this point here is, then basically that will give us the distance from the x-axis to that point. We will get that distance, and then you can add it to this 23 inches, which we already know is the thickness of the glass. So the thing is, we need to find this point, or you can think of this point, it doesn't matter. It's going to be the same on both sides. So if we can find one of these points to help us out, then we know what this distance is going to be, and then adding it to the 23 inches here will help us come up with our total thickness on that outside edge. So what we're going to do here is, okay, let me show you if I can draw this as our graph over here. Okay, so this is our x-axis. Our mirror is placed somewhat like this, right? Okay, this is our mirror. Now we know this distance here is 23 inches, so you can kind of think of this as being negative 23, since we're placing this below the x-axis, but basically that tells us this distance here is 23 inches, right? Now the one other thing they told us is that the glass mirror is 200 inches in diameter. So you know that's this distance right over here. So this width of our glass is 200 inches. So if our vertex right here is at 0, 0, then that means this number here is going to be positive 100 on the x-axis, and this number here is going to be negative 100 on the x-axis. So that will add up to a total of 200 inches, which will give us the diameter of our mirror. So let's say if I am interested in finding this point. Now this point corresponds to the 100 on my x-axis, and I am trying to find out what its y coordinate is. So I already know the equation for this parabola. So if I already know the equation for this parabola, then I can just plug in this as my x value, and it can help me find what my missing y value is going to be. So that's the first part we are going to do, is we are going to take our equation. Come on, buddy, there we go. 1 divided by 2,640 x squared. So like I said, we know our x value is going to be 100, because that's going to match this positive 100 on my x-axis here. So this will end up giving us a value of, and let me see, so that's 100 squared times 1 over 2640. So this is coming out to be 3.7878, and it looks like that 7878 is repeating. Okay, so that's going to give you this y value here as 3.7878 repeating. There we go. Okay, so we now know this distance is going to be 3.78 inches, and then we have our distance here, which is 23 inches. So then we can add 23 inches with this 3.7878 repeating. So that will come out to be 26.7878. And of course we don't want to keep it repeating, so let's go ahead and round it to 1 decimal place, and this will come out to be 26.8 inches as the thickness at the outside edge. Okay, so once you have that equation of the parabola, not only does it help us to figure out what the shape of our parabola is going to be, but as you can see, that also helped us calculate what that thickness of the parabola would also come out to be. So you can kind of see how this math works out in this case. So there are just so many different things that we can do with this calculation when you look at the geometric form. So basically what I want to reiterate is that this equation over here basically helps us come up with this thickness of the 3.7878 that we got. So just kind of keep that in mind, okay? Alrighty, folks. So this was our example for how the mirror in a telescope is designed based on what equation. So this was our last example here in section 7.1. So as always, guys, obviously look through the handout and the video and let me know if you have any questions on this, and then I will answer any of the questions you might have in class. So be careful, stay safe, and I'll see you in class next time, guys. Take care. Bye-bye.